Wideband cavity-backed patch antenna for air surveillance radar application. Abstract: this paper describes a compact rectangular patch antenna design for achieving the required bandwidth. The antenna is a probe-fed microstrip antenna printed on a RT Duroid 5880 layer, .r equals 2.2 thickness equals 1.6 mm, enclosed in a cavity. In the design process, the effect of cavity on the impedance bandwidth of the antenna is first studied, and then an additional loading to cavity structure is added such that it resonates at the required frequency band of interest. The antenna is working for 400 MHz bandwidth, 12%. With return loss -10 dB in S-band and with an antenna element gain of more than 7.2 dB. This design is simulated in FEM-based 3D simulator HFSS. KeywordsCavity patch antenna, probe feed, patches, loading. Introduction. Microstrip antennas are used for numerous applications because of advantages like low profile, ease of fabrication, low weight, etc., but as these antennas are resonant, they are limited in bandwidth. Various techniques are available to improve the bandwidth, both impedance bandwidth and pattern bandwidth. These techniques include different feed techniques, stacked patches, adding parasitic, etc. It is shown that bandwidth can be increased to 60% by using special techniques. Another basic advantage of microstrip patch antenna is that dual frequency operation is easily achieved, and if the resonances are brought closer to each other, these resonances merge to give a wider bandwidth. In this paper, design is carried out by using a cavity-backed probe-fed rectangular patch antenna. Cavity-backed patch antennas are widely used in today's applications as they possess inherent advantages like reduced sizes, suppressed surface waves, and hence low mutual coupling in array configurations. But adding cavity to a patch antenna limits the bandwidth, as cavities are considered to be resonant structures. Microstrip patch with loaded cavity are used to characterize and improve the bandwidth for the required frequency of operation. 2. Design and working principle. The antenna uses 3 different configurations, namely probe feeding and cavity backing and loading. Probe feeding is used in the patch geometry as feeding in presence of cavity is relative easy, and also coupling to the patch is better because of direct transfer of energy. The antenna configuration is shown below. WP, W, LP, L, IMG_20200925_113307.jpg. Fig 1. Cavity patch antenna configuration, top. IMG_20200925_113146.jpg. Fig.2. Cavity patch antenna configuration, side view. H. D. IMG_20200925_113232.jpg. Fig 3. Cavity patch antenna configuration, top view. W equals 68.4 mm, WP equals 41.1 mm, L equals 39.3 mm, LP equals 22.6 mm, D equals 9.8 mm, depth of cavity DC equals 7.6 mm, position of probe pin from edge of patch is XO equals 1.7 mm. The coupling of energy to probe-fed antenna is given by *1. Effective dielectric constant for different layers is calculated using 1 equals dash plus 2. H denotes the height of patch. Equals plus dash slash 3. Design steps are as follows. 1. Calculation of resonant frequency assuming dominant TM10 mode. Equals slash plus dot slash V slash 4. Where L. Empirical correction factor. R is per 1 dot. CH4 page 267. 2. The effect of cavity on patch resonance is given by 3. It is observed that effective dielectric constant changes due to the proximity of cavity walls on the patch, which in turn changes the patch resonance. Initial design is carried without a cavity and resonant length is determined as per resonant frequency. Now cavity is introduced and a shift in the patch resonance to lower frequency is observed. Hence the patch resonant frequency, FR, is reoptimized with new length. Since effective dielectric constant is increase S by an amount equal to EQ.5, the length, less than equals *5. K is determined by using 3. Coupling between the patch and loaded cavity is best understood from the electric field distributions on different surface planes as shown in Figure 4, Figure 5, and Figure 6. Fig 4. Electric field pattern in XZ plane. Fig 5. Electric field pattern in YZ plane. Fig 6. Electric field pattern in XY plane. Energy coupling between the patch and cavity is strongly influenced by the loading structures in cavity. The structure is simulated and optimized in 3DM Simulator and CHFSS. 3 Results and discussions. The antenna is optimized in the frequency range of 3.1 to 3.5 GHz, 400 MHz. The figure 7 represents the simulated and measured results of return loss. The return loss is observed to better than 10 dB over the full bandwidth. Fig 7. Simulated and measured return loss in dB. Fig 8. Simulated and measured azimuth radiation pattern. Measured and simulated azimuth radiation patterns is shown in figure 8. The simulated gain is 7.1 dB and beam width is varying from 60.7 degree to 70.4 degree. The measured gain is 7.2 dB and beam width is varying from 58.4 degree to 63.8 degree. Fig 9. Simulated and measured elevation radiation patterns. In the above figure 9 measured and simulated elevation radiation patterns is depicted. The simulated gain is 7.3 dB and beam width is varying from 78.5 degree to 88.5 degree. The measured gain is 7.2 dB and beam width is varying from 95.2 degree to 98.1 degree. Table I simulated/measured radiation pattern comparison. The measured and simulated antenna parameters are summarized in the table 1 above. For conclusion, a compact rectangular patch with loaded cavity-backed antenna is designed for required bandwidth, and detailed study of the effect of cavity on patch resonances is observed. The antenna has a very useful application as a phased array since cavities prevent the surface wave propagation, thus eliminating skin blindness. The skin loss can be made lesser by varying the available degrees of freedom. There is close coherence between simulated and measured results. Acknowledgement. The author would like to thank GMNSII Shri Umesh KSNA.G.MSMT Dharani B for their continuous support and permission to publish this work.